So clearly, two electrons can never be in the same state because that causes their combined wave function to disappear. Now the only components making up the dynamical state in the atom is the shell it occupies, and another property that electrons have called spin. You can think of electrons as little spinning tops if that helps. And these electron tops can spin in only two ways: upright or upside down, which can make them distinguishable. So the end result is that two and only two electrons can occupy each shell in an atom, one with spin up and the other with spin down. Other electrons in the atom must occupy higher and higher shells. This is called the Pauli exclusion principle, first espoused by Wolfgang Pauli. Without this exclusion, all electrons would occupy the lowest energy state, and atoms would behave very differently, and the universe would be a very different place. The fact is that the property called spin is quantized as well. No big surprise. And all the particles fall into one of two different families because of this. Those particles that have spin equal to 1/2, or 3/2, or 5/2, and so on, form the family called fermions. The name comes from Enrique Fermion, who along with Paul Dirac developed the statistical methods of dealing with them. Fermions are said to have half-integral spin. And as indicated above, electrons, quarks, protons, neutrons are all in this family. The other family of particles have spin equal to 0, 1, 2, 3, and so on. They are called bosons, after Satyendra Bose, who along with Einstein developed the statistics for dealing with this family. Unlike fermions, which must obey the Pauli exclusion principle, bosons do not. Groups of multiple bosons will all gather in the lowest available energy state. Photons, gluons, gravitons all fall into this family. If bosons had to obey the exclusion principle, many modern marvels could not exist. Like lasers, which require that huge numbers of photons be in the same state at the same time, and again, the universe would be a very different place. Where's the weird, you ask? Once you get past the existence coming and going, and virtual particles, and uncertainty, and exclusion, most of the weird stuff in quantum physics comes from what is known as entanglement, and subsequently wave function collapse. When two or more particles interact, their wave function becomes entangled in such a way that some properties of each are now depending on what happens to the other particle. Then these particles can be carefully separated, while in careful isolation to distant locations, but as long as they're not disturbed, they are still entangled and still have properties dependent on each other. Then, when one particle is examined to see what the individual property might be, the wave function instantly disentangles. Physicists would say this wave function collapses. Instantly, the other particle has its codependent properties disentangled and determined. Here is an example. we can set up a source to emit electrons in pairs, with their spins dependent on and opposite from one another. Now, neither electron knows what spin state it is in. Both are flip-flopping back and forth between spin up and spin down. But their wave functions are entangled, so that whenever one of the electrons is disturbed and settles into one of the spin states, say spin up, the other electron instantly settles into spin down state. And this instantly occurring collapse happens whether the electrons are next to each other or on the opposite side of the planet. And while some of that is truly weird, a host of modern technologies are beginning to rely heavily on this weirdness. Quantum computing, quantum cryptography, and quantum teleportation, to name a few. And because of the work they are doing in these fields and others, many scientists have little doubt that this particular quantum weirdness is an actual phenomenon. Real entanglement experiments have now been done where the separations have been over 100 kilometers, proving that distance does not destroy entanglement. This is analog. This is digital. This is analog. This is digital. This is analog. This is digital. If it is continuous, it is analog. If it is granular, it is digital. The current trend in audio, video, and communication technologies is to go digital. Instead of a continuum of color in video devices, we are limited to some finite number of colors. Instead of a continuous picture, our photo is divided into pixels. Instead of just any frequency in audio, we are limited to specific steps. This is very much like the universe in the realm of the small. The entire universe went digital about 14 billion years before we thought of it. Space, time, energy, momentum are all granular. There are only certain specific values allowed, and this granularity is accurately described by quantum mechanics.